The concept of parallel universes might seem like a plot from a science fiction novel, yet it is deeply rooted in scientific inquiry. The multiverse theory suggests that our universe is not the only one. Instead, there are countless others, each with different laws of physics, constants, and possibly even different versions of ourselves. But how did this astonishing idea come about? The origins can be traced back to the early 20th century when the field of quantum mechanics began to blossom. Quantum mechanics introduced a level of unpredictability into the realm of physics that was previously unheard of. One of the pivotal figures in this narrative is Hugh Everett III, a young physicist whose groundbreaking doctoral thesis in 1957 posited the many worlds interpretation of quantum mechanics. According to this interpretation, every quantum event spawns a branching of the universe into multiple paths, creating a separate universe for each possibility. If you imagine a decision point, like choosing a career path, in one universe you may become a doctor, while in another, you become an artist. This bizarre idea of infinite possibilities stirred significant debate and skepticism in the scientific community. An early supporter of Everett's theory was the renowned physicist Richard Feynman, who championed the concept of superposition, a key ingredient for the many worlds interpretation. Feynman famously claimed that particles could exist in multiple states at once until observed. This laid the groundwork for considering an infinite number of outcomes for every single event in the universe, opening the door for parallel realities. As we transitioned through the decades, the multiverse theory gained traction. In the 1980s, cosmologist Alan Guth introduced the inflationary theory, suggesting that our universe underwent rapid expansion after the Big Bang. This theory implied that if inflation occurred in one area, other regions could experience diverging paths, leading to countless bubble universes, each with distinct characteristics. To put it into more intuitive terms, you can think of a loaf of bread. Each slice is a different universe, and the expansion of the bread itself represents the moments in time where new universes are created. Each bubble universe can develop its own set of physical laws and characteristics. While the multiverse theory is still controversial and not universally accepted, it continues to change the way we perceive our existence in the cosmos. The idea challenges our understanding of reality and forces us to contemplate the possibilities of what if. The implications are staggering. If there are infinite universes, then every possibility is realized somewhere. But how can we find evidence for these other realities? Quantum mechanics has allowed scientists to explore realms once thought impossible. For instance, the concept of quantum foam proposes that at the smallest scales of the universe, think Planck length, it isn't just empty space. Instead, it's a seething, turbulent brew of quantum fluctuations that might give rise to new universes. Moreover, researchers are conducting experiments to unveil these secrets. The Large Hadron Collider, LHC, in Switzerland is one of the most ambitious projects ever undertaken. It accelerates particles to near the speed of light, attempting to recreate conditions similar to those just after the Big Bang. Some theorists hypothesize that within the data collected, there might be evidence hinting at other dimensions and universes. Additionally, the quest for a unified theory has scientists examining string theory, a leading candidate to merge general relativity and quantum mechanics. String theory suggests that the fundamental building blocks of the universe aren't particles, but tiny vibrating strings. These strings could exist in multiple dimensions beyond our observable reality, laying the groundwork for alternate universes. As we continue to explore quantum mechanics, the boundaries between traditional understandings of reality and the cosmic wonder of multiple universes become increasingly blurred. But if parallel universes exist, how may we discover them? How can we bridge the gap between our universe and those we cannot see? If quantum mechanics is the foundation upon which we build our understanding of parallel universes, then string theory offers the framework for how these universes might interact. In the 1980s, string theory emerged as a groundbreaking approach that described particles not as points, but as tiny, one-dimensional strings that vibrate at different frequencies. This opened a fascinating discussion about the role of additional dimensions in our universe. In conventional physics, we understand the universe in 3 spatial dimensions and 1 time dimension. However, string theory suggests that there could be many more dimensions, possibly up to 10 or 11. These extra dimensions could be compactified or curled up so tightly that they remain hidden from our direct observation. But how does this relate to the multiverse? When strings vibrate in different ways, they can give rise to different particle types and, consequently, different laws of physics. In a multidimensional universe, it's conceivable that there are regions where these strings vibrate in ways leading to entirely different universes with drastically different properties. Consider the concept of the cosmic landscape. This term describes the multitude of possible vacuums that string theory allows. Each vacuum corresponds to a different universe with its distinct laws of physics. Some universes may support life, while others could be inhospitable. In this vast landscape, our universe is just one of many, potentially among hundreds of billions of other universes. Notably, this idea of a cosmic landscape has sparked fierce intellectual debates. One significant challenge is that these alternate universes may be fundamentally disconnected from our own, making them unobservable and untestable. Critics argue that if these universes cannot be accessed or observed in any way, we cannot claim that they exist scientifically. Yet others advocate for exploring the cosmic landscape through indirect evidence. For instance, if one universe has a different set of physical constants, it may influence the outcomes we observe in our own universe. Perhaps cosmic rays or gravitational waves could carry signatures of interactions between our universe and neighboring ones. In this context, understanding quantum fluctuations becomes essential. Quantum fluctuations might ripple through dimensions, creating detectable events in our universe that hint at the presence of others. As we explore this cosmic landscape, we confront profound questions about existence, life, and the nature of reality itself. If there are infinitely many universes, what does it mean for our universe's singularity? Are we merely one thread in an ever-expanding tapestry of existence? The answers may lie not only in theoretical physics but also in our philosophical understanding of self and existence. As scientists navigate the complexities of string theory and the cosmic landscape, we are left wondering, could we ever bridge the divide between these universes, and if so, what would that mean for humanity? While the concept of parallel universes may seem abstract, researchers in cosmology and astrophysics are continually seeking evidence that could support the existence of these alternate realities. One of the promising avenues for this exploration involves cosmic microwave background radiation, or CMB. This relic radiation is the afterglow of the Big Bang and carries a wealth of information about our universe's formative years. Astrophysicists have observed anomalies in the CMB that hint at something more profound. Some of these anomalies appear as unusual cold or hot spots that cannot be easily explained by current models of a homogeneous universe. Researchers theorize that these fluctuations could be evidence of interactions between our universe and neighboring universes in a multiverse scenario. Moreover, the discovery of dark energy has further complicated our understanding of the universe's expansion. Dark energy is an enigmatic force that drives the acceleration of the universe's expansion, and it raises questions about the nature of our universe. Some theorists suggest that dark energy might have different properties in other universes, leading to different expansion rates and cosmic structures. Furthermore, gravitational waves, ripples in spacetime caused by cataclysmic events, may also provide tantalizing clues supporting the existence of parallel universes. Detecting these waves has opened new windows for understanding cosmic events and the potential for revealing interactions with other dimensions or universes. LIGO, the Laser Interferometer Gravitational Wave Observatory, is at the forefront of this research. If signs of multidimensional interactions are detected, it could provide significant support for the multiverse hypothesis. As we investigate these cosmic phenomena, we encounter profound implications for our understanding of reality. If alternate universes exist, what are the consequences for scientific principles? It challenges the very foundation of science, questioning whether our established laws apply universally, or only within our singular reality. This brings us to the role of experimentation and the essence of what defines scientific inquiry. The existence of parallel universes raises fundamental questions about fate, free will, and the nature of existence itself. In a multiverse, everything and nothing coexist. If there are infinite versions of ourselves making different choices, then our notion of self becomes increasingly elusive. How do we reconcile the idea of individual choice with the existence of countless others? The implications reverberate through philosophy, psychology, and even ethics. As we stand on the precipice of discovery in cosmology and astrophysics, we find ourselves questioning, what if we could prove the existence of these parallel universes? As we explore the scientific dimensions of parallel universes, we must also confront the profound philosophical questions they raise. The multiverse theory does not merely challenge our understanding of physics, it alters our perception of ourselves and our existence. If infinite realities exist, how do we come to terms with our singular experience? One of the most compelling philosophical implications revolves around the concept of free will. If every choice we make spawns a new universe, do we truly have agency in our actions? Are we merely players in a cosmic game where every outcome exists simultaneously? This notion is echoed in the works of existential philosophers like Jean-Paul Sartre, who emphasized the importance of choice and responsibility. Moreover, the multiverse raises ethical questions about morality. If different versions of ourselves exist in alternate realities, how do we navigate right and wrong? Is our moral framework universal, or does it shift depending on the universe we inhabit? For instance, every decision we make in our lives could lead to both virtuous and malevolent outcomes across various universes. Understanding morality becomes complex. It can lead us to question whether true altruism exists if our choices always yield different results in other realities. Add to this the concept of identity and selfhood. If there are countless iterations of ourselves leading different lives, what does it mean to be you? The idea of self becomes fragmented, as we may possess multiple identities across different realities. This symbolizes a deeper connection to the cosmic fabric of existence, transcending our conventional understanding of individuality. Furthermore, the multiverse posits a paradigm shift in our approach to knowledge and discovery. If reality is fluid and ever-changing, then the pursuit of certainty becomes more elusive. The multiverse suggests that our scientific principles are not absolute, they may only apply to a specific realm, leaving us to grapple with uncertainties in our understanding of the universe. By expanding our understanding of reality, we are invited to embrace ambiguity and complexity. As we ponder these philosophical implications, we must also consider the human experience. Are we alone in this vast cosmos, or do our counterparts in other universes share similar struggles, dreams, and aspirations? If parallel universes exist, we may be part of a collective existence that transcends our singular lives. We are left with one fundamental question: what does it mean to truly exist? The answers may be multifaceted, reflecting our individual and collective journeys through reality. Additionally, as we grapple with our place in the multiverse, we recognize the profound beauty of existence itself and the interconnectedness of all beings. Will our quest for knowledge ever unveil the secrets of the multiverse? And if so, what revelations lie in store for humanity? Imagine a world where every decision you make spawns a different universe, each with its own reality. This is the premise of the many worlds interpretation, a striking concept that stems from quantum mechanics. In the early 1950s, physicist Hugh Everett III introduced this idea, shaking the very foundations of how we understand reality. According to the many worlds interpretation, every possible outcome of a quantum event actually occurs but in different, branching realities. To illustrate this, let's consider a simple example, the classic Schrödinger's cat thought experiment. In this scenario, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, and the cat dies. But until we open the box, the cat is considered to be both alive and dead simultaneously. In the many worlds interpretation, when the atom decays, the universe splits into two branches, one where the cat is alive and one where it is dead. This idea sounds far-fetched, but it has profound implications. It challenges our perceptions of reality and questions the uniqueness of our experiences. If every decision creates a new universe, what does that mean for concepts like free will and destiny? Are we merely players in an endless game with infinite outcomes? Scientists have been poking holes in classical interpretations of quantum mechanics for decades, and many worlds is gaining traction not just for its imaginative reach, but also for its ability to elegantly solve some lingering problems within quantum theory. For instance, it resolves the measurement problem, explaining why we observe a definite outcome when we measure quantum states. In this view, we simply find ourselves in one of the many branches that correspond to that outcome. Despite its allure, many worlds faces skepticism. Critics argue that it struggles with empirical verification. How do we test theories about realities we cannot observe? Yet, proponents assert that the mathematical framework of quantum mechanics supports the interpretation. As we dive deeper into this intriguing realm, we cannot ignore the philosophical debates it stirs. Some argue that the many worlds interpretation offers a solution to the paradoxes of time travel, while others claim it undermines the very essence of our existence. If every choice creates a new you, does that dilute the meaning of your life? These questions leave us at the crossroads of science and philosophy, daring us to rethink who we are in an infinite cosmos. Concluding this chapter, we realize that the notion of existing in multiple worlds is both thrilling and daunting. As we ponder the concept of branching realities, we must now ask ourselves, if we could hop between these dimensions, would we dare to explore the choices not made? As we journey forward, it's crucial to investigate the evidence supporting the multiverse theory and the controversies that arise from it. In the scientific community, consensus is often seen as a cornerstone of advancement. However, the multiverse theory remains a hotbed of debate. One of the strongest arguments for the multiverse comes from cosmic inflation, a theory proposed by Alan Guth in the 1980s. Cosmic inflation suggests that the universe underwent a rapid expansion right after the Big Bang. This theory not only explains the uniformity of the cosmos but also implies the existence of other bubble universes, forming in regions of space that stopped inflating at different times. To illustrate, think of our universe as part of a vast foam. Each bubble represents a different universe, with varying physical laws and constants. Some might be similar to ours, while others could be entirely alien. This scenario presents a tantalizing possibility that could align with our observations of cosmic microwave background radiation, a remnant echo of the Big Bang. However, not all physicists are on board with this interpretation. Critics argue that the multiverse hypothesis is inherently untestable. If these other universes are entirely separate and inaccessible, how do we confirm or deny their existence? This poses a significant challenge for proponents who aim to secure empirical data. Additionally, we encounter the anthropic principle, which suggests that the universe's characteristics allow for the existence of observers like us. In a multiverse scenario, our universe is just one of many that happen to support life. The critics caution that this explanation can verge on the tautological, leading to potential philosophical pitfalls. Among the controversies is the question of what constitutes science. Some argue that the multiverse theory, lacking testable predictions, borders more on philosophy than science. Physicist Richard David asserts that the multiverse must be rejected unless there are ways to probe its existence through indirect means. In contrast, others advocate for a broader definition of science that includes theories not readily falsifiable. The multiverse has sparked intense debate over the very nature of scientific inquiry. Is it enough to have a robust mathematical framework, or must our theories yield observable consequences? As this chapter draws to a close, the contradictions between evidence and speculation remind us that science is an ever-evolving pursuit. The questions surrounding the multiverse keep us striving for understanding, awareness that the journey itself is just as significant as the arrival. As we ponder these debates, we can't help but wonder, could the key to understanding our universe lie in these unseen realms? Parallel universes are not just a staple of scientific discourse, they have infiltrated our popular culture and shaped how we consume narratives. From literature to blockbuster films, the concept of alternate realities resonates with audiences, reflecting our deepest curiosities and fears. Consider the sci-fi classics like Philip K. Dick's The Man in the High Castle, where an alternate history is explored in a world where the Axis powers won World War II. This narrative not only captivates audiences but serves as a philosophical exploration of fate and free will in a universe defined by different choices. In film, we see a plethora of interpretations. Movies like Interstellar dive into the fabric of space-time, while Doctor Strange introduces viewers to a complex multiverse where every choice creates identical but divergent realities. These portrayals ignite imaginations and offer a visual exploration of theoretical physics, albeit through a creative lens. Television series such as Rick and Morty and Fringe delve further into these ideas, exploring both comedic and dramatic consequences of parallel universes. Rick and Morty humorously unpacks the chaos that ensues from interdimensional travel, questioning the value of choices in a universe filled with infinite options. On the other hand, Fringe takes a more serious tone, using parallel realities to tackle ethical dilemmas. These stories resonate because they mirror our existential queries. What if our lives took a different path? What if our choices weren't just singular moments but catalysts for the birth of new realities? This fascination with the multiverse reflects a collective yearning to understand our place in an intricate cosmos. As we indulge in these narratives, it becomes apparent that science fiction serves as a bridge between complex scientific theories and the public consciousness. It invites us to think critically about the implications of parallel universes, often sparking dialogue around science, philosophy, and ethics. However, we must discern between entertainment and scientific rigor. While fiction can inspire, it should not replace a grounded understanding of the science at play. As we end this chapter, we are left contemplating the power of storytelling in shaping our perceptions of the universe. The multiverse is not just an abstract concept but a narrative thread interwoven through the fabric of our cultural zeitgeist. As we move forward, let's wonder how stories will continue to evolve as we venture deeper into the unknown mysteries of reality. As we navigate through the intricate web of theories and cultural interpretations surrounding parallel universes, we arrive at a crucial juncture: the future of multiverse research. What lies ahead in the quest to understand whether alternate realities exist? The next decade promises to be pivotal for cosmology and quantum physics. With advancements in technology, scientists are poised to gather unprecedented data that could either bolster or challenge the multiverse theory. For instance, observatories like the James Webb Space Telescope, launched in late 2021, are designed to peer deeper into space than ever before. Its observations might provide insights into cosmic inflation and the conditions of the early universe. Moreover, particle physics experiments at facilities like CERN aim to unravel the mysteries of the universe. The Large Hadron Collider seeks to investigate the fundamental particles that compose our reality. If multiverse theories hold weight, we may find indirect evidence through interactions or anomalies we cannot yet explain. Quantum computing also stands at the forefront of revolutionizing our understanding of the universe. By harnessing the principles of quantum mechanics, researchers could simulate complex multiverse scenarios, allowing them to explore infinite possibilities within a controlled environment. Nevertheless, the path forward is not without skepticism. As we push the boundaries of our understanding, ethical considerations become paramount. Should we continue down the rabbit hole of theoretical exploration without tangible results? The scientific community must grapple with these questions as they strive for both understanding and responsibility. As we consider the journey of multiverse research, it becomes evident that the pursuit is not merely about finding answers but also fostering curiosity. It encourages us to look beyond the observable and embrace the complexities of our existence. The possibilities are endless, as are the mysteries that reside within the multiverse. With every question we answer, new ones arise. As we conclude this chapter, we must reflect on our desire for knowledge. Perhaps, it is not necessarily about discovering alternate universes but understanding our own universe better, as each piece of knowledge can illuminate the greater tapestry of existence. What revelations await us in this relentless pursuit? As we conclude our exploration into the enigmatic world of parallel universes, we are left with more questions than answers. The multiverse theory, steeped in scientific inquiry and philosophical contemplation, challenges us to redefine the boundaries of reality. Every chapter has revealed a facet of existence that intertwines with our understanding of life, reality, and the choices we make. The many worlds interpretation offers a perspective that is as mind-bending as it is liberating. It encourages us to consider that every choice creates ripples across an infinite ocean of potential realities, each uniquely unfolding. Yet, as we delve deeper, we confront the controversies and debates that surround the multiverse theory. The quest for empirical evidence remains a formidable challenge. While the multiverse opens a door to stunning possibilities, we must approach these theories with a critical mind, balancing wonder with skepticism. Popular culture has helped bridge the gap between the complex science of parallel universes and our everyday lives. Through films, literature, and television, we engage with profound questions that resonate with the human experience. This intersection of science and storytelling invites us to explore our identity and purpose within the vast expanse of existence. As we stand at the precipice of scientific advancement, the future of multiverse research beckons us to embrace uncertainty. Technological breakthroughs promise to reshape our understanding and perhaps even guide us toward answers we have yet to conceive. In this brave new world, our innate curiosity fuels the fire of discovery, pushing us beyond what we think we know. Ultimately, the multiverse invites us to embrace the unknown. While our grasp of reality remains incomplete, it is precisely this uncertainty that fuels our passion for exploration. As we ponder the universes that may lie beyond our perception, we are reminded that the beauty of existence is found not just in answers but in the journey itself. So, as we step away from this investigation, let us continue to question, explore, and wonder. The multiverse may be a tapestry of infinite possibilities, but it is our curiosity that will weave the threads of discovery, leading us to new depths of understanding in the cosmos and ourselves. What will you explore next in the vast universe that awaits? As we delve deeper into the fabric of our universe, we cannot ignore the enigmatic forces that seem to govern it, dark matter and dark energy. These two components make up about 95% of the total mass energy content of the universe, yet remain largely invisible and mysterious. Let's start with dark matter, a substance that does not emit light or energy, making it virtually undetectable by conventional means. Still, its existence can be inferred through gravitational effects on visible matter. For instance, the rotation curves of spiral galaxies reveal that stars on the outer edges are moving much faster than they should if only visible matter were present. This discrepancy leads scientists to conclude that there must be some form of unseen mass exerting gravitational pull, hence, dark matter. In a groundbreaking study in 1933, astronomer Fritz Zwicky used the Coma cluster of galaxies to argue for the presence of dark matter. His observations showed that the galaxies were moving faster than expected, suggesting they were bound by a gravitational force much greater than the visible mass could explain. Fast forward to today, and the evidence for dark matter has only strengthened, with research showing its influence in the cosmic microwave background radiation and large-scale structures of the universe. Now, on the other side of this mysterious coin lies dark energy. This force is believed to be responsible for the accelerating expansion of the universe. In the late 1990s, two independent teams of astronomers studying distant supernovae made a startling discovery: the universe is not just expanding, it's accelerating. The force driving this acceleration was named dark energy, which makes up roughly 68% of the cosmos. But what exactly is dark energy? It remains one of the biggest unsolved mysteries in physics. Some theories suggest it could be a constant force, a feature of empty space that grows with the universe, while others propose it might be a dynamic field that changes over time. This complexity adds a rich layer to the multiverse theory. If our universe is one of many, differing amounts of dark energy could lead to various cosmic fates in parallel universes. For instance, in a universe rich in dark energy, expansion might continue indefinitely, leading to a big freeze, whereas in a universe with less dark energy, gravity could cause a big crunch. The implications are profound. If dark energy is a constant, then in other universes with differing constants, life as we know it may not even exist. Ultimately, the exploration of dark matter and dark energy is vital, not just for understanding our own universe, but potentially for explaining how other universes may operate. As we continue to study these cosmic mysteries, researchers are forging ahead with new telescopes and experiments designed to unveil the secrets they hold. What will we discover about dark matter and dark energy? What can their nature tell us about the very structure of reality? As we stand on the brink of new understandings, the potential for swirling waves of parallel realities grows ever more immediate. Black holes have long captured the imagination of scientists and enthusiasts alike. These enigmatic regions of space, where gravity pulls so much that even light cannot escape, are more than just cosmic vacuum cleaners. Recent theories suggest that black holes may hold clues to the existence of parallel universes. The most discussed theory comes from the physicist Kip Thorne, who posited that the singularity at the center of a black hole may serve as a bridge to another universe. When a massive star collapses, it forms a black hole, and within it lies a point of infinite density called a singularity, cradled by an event horizon. Beyond this point, classical physics breaks down, and strange phenomena may occur. One fascinating idea is that if something were to fall into a black hole, it might not just be obliterated but instead might emerge from a white hole, the theoretical opposite of a black hole, in a different universe. This leads us to the concept of wormholes, theoretical passages through spacetime that could create shortcuts between distant parts of the universe and perhaps even connect different universes. In 2016, gravitational waves were detected for the first time, providing a groundbreaking step in understanding black hole dynamics. The collaboration between LIGO and Virgo observatories revealed insights into merging black holes, propelling our understanding of how black holes behave. Interestingly, a scientist named Andrew Strominger proposed that black holes could be connected to the fabric of string theory, suggesting that the event horizon of a black hole could act as a boundary separating our universe from others. This interaction raises questions. Could information about the contents of one universe be stored in the fabric of another? And if so, what does this mean for the laws of physics? To complicate matters further, researchers are exploring the holographic principle, which posits that all information contained in a volume of space can be represented as a hologram on the boundary of that space. Some theorists even suggest that our own universe could be a projection from a two-dimensional surface, with black holes functioning as portals leading to other projections, potentially other universes. As we continue to study the nature of black holes, we may uncover truths that transcend our understanding of space and time. Each discovery challenges us to reconsider our position in the universe and the nature of existence itself. Could black holes indeed be gateways to other worlds? Or are they simply endpoints, the final chapter of a star's life? The exploration of these cosmic giants is a journey still in its infancy, and as we push the boundaries of our knowledge, the potential for uncovering the multiverse deepens. In the realm of science, the intersection of technology and theory can lead to revolutionary insights. As our understanding of the cosmos expands, so too does the arsenal of tools we utilize to explore it. Emerging technologies are reshaping the landscape of multiverse research, bridging gaps between theoretical physics and practical observation. One such technology is the advent of quantum computing, which holds the potential to solve complex equations that have long baffled our best minds. Traditional computers operate on binary principles, manipulating bits of information in a linear fashion. Quantum computers, on the other hand, leverage the properties of quantum bits, or qubits, which can exist in multiple states simultaneously. This means they can process vast amounts of data and perform calculations at unprecedented speeds. For multiverse researchers, this capability could prove vital. Complex simulations that model the interactions between different universes and their variables require immense computational powers. In the near future, quantum computing might enable physicists to run scenarios that analyze how different constants might affect the physical laws of alternate realities. Another groundbreaking tool is the development of advanced telescopes and detection methods aimed at observing cosmic phenomena that hint at the existence of other universes. The James Webb Space Telescope, launched in late 2021, exemplifies this shift. Its ability to capture detailed images of the early universe provides a window into events that occurred shortly after the Big Bang. Analyses of cosmic inflation and the cosmic microwave background radiation could lead to indirect evidence of other universes. Already, scientists have gathered data suggesting ripples from our universe's expansion could be remnants of interactions with neighboring universes. Artificial intelligence is also playing a pivotal role in interpreting this vast amount of data. AI algorithms can analyze patterns and anomalies in the data collected from telescopes, searching for signs that might indicate the presence of a multiverse. As we gear up for future missions and projects, collaboration among scientists, engineers, and technologists is paramount. New research institutions are emerging, specifically aimed at exploring these complex questions about the multiverse. In addition to observational breakthroughs, advancements in particle physics at facilities such as the Large Hadron Collider, LHC, contribute to our understanding of fundamental forces, potentially unlocking secrets about the structure and behavior of multiple universes. As particles collide at nearly the speed of light, researchers explore conditions that may mirror those of our universe's inception. The impact of these emerging technologies on multiverse research is immense. Each breakthrough establishes not just a new understanding of the cosmos but also a framework for future inquiries. With each discovery, we inch closer to deciphering the tapestry of realities woven together in this grand cosmic story. What possibilities lie ahead as technology continues to evolve? How will our understanding of parallel universes grow as new discoveries unfold? The answers remain some of the most tantalizing mysteries waiting to be uncovered. When we think about the nature of parallel universes, it's impossible to ignore the concept of quantum entanglement, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. In essence, quantum entanglement suggests that particles can become connected, such that the state of one particle is instantly correlated with the state of another, no matter how far apart they are. This strange linkage raises pivotal questions about our understanding of the universe and reality itself. To comprehend entanglement's significance, we need to delve into the experiments that demonstrate this bizarre behavior. For instance, the famous Bell's theorem experiment conducted in the 1960s provided strong evidence that quantum mechanics cannot be reconciled with classical physics. When entangled particles are measured, the results show correlations that defy conventional explanations of local realism, leading to the conclusion that entangled particles exist in a state that transcends our familiar universe. Consider the work of physicist Alain Aspect and his team who conducted experiments in the 1980s that tested Bell's inequalities. Their results provided empirical evidence supporting quantum entanglement and indicated that particles could indeed be connected across vast distances. What does this mean for parallel universes? The interconnectedness of entangled particles could suggest that variations of reality are not just hypothetical but are part of a more complex framework of interconnected universes. One intriguing implication of entanglement lies in the idea of information transfer. If information can be shared instantaneously between entangled particles, could this mean that knowledge from parallel universes can influence our decisions or realities? This aligns with the many worlds interpretation of quantum mechanics, proposing that each decision creates a branching of realities, potentially impacting entangled states across multiple universes. There are numerous real-world applications of quantum entanglement, particularly in quantum computing and cryptography. For example, entangled particles can be used to create ultra-secure communication channels that are theoretically immune to eavesdropping. These developments not only push the boundaries of technological innovation but also reinforce the idea of a more interconnected universe. In the realm of theoretical physics, some researchers are exploring how entanglement could provide a bridge to understanding other dimensions or parallel universes. Notable physicists, including Sean Carroll, theorize that quantum entanglement could be the fabric that connects different realities, suggesting that every particle and event may have a dual existence in multiple universes. This perspective opens up exciting avenues for future exploration and discussion. As you ponder the implications of quantum entanglement on the multiverse, consider these questions. Could entangled particles serve as conduits for information across the multiverse? How might our understanding of reality shift if we accept that our decisions resonate beyond our universe? As we navigate through these profound questions, the possibilities seem limitless, and engaging with them is essential for anyone curious about the nature of existence and the cosmos. In conclusion, quantum entanglement not only challenges classical physics but also offers tantalizing possibilities about the interconnectedness of parallel worlds, beckoning us to further investigate the deeper layers of reality. Gravity is one of the fundamental forces shaping our universe, and its role in the context of parallel universes is a critical aspect of ongoing scientific inquiry. Sir Isaac Newton introduced gravity as a force that draws objects toward one another, while Albert Einstein expanded this notion with his theory of general relativity, which depicts gravity as the curvature of spacetime created by mass. But how does gravity intersect with the concept of parallel universes? One compelling explanation arises from the notion that our universe may exist within a larger multiverse governed by different gravitational laws. Various models suggest that slight variations in gravitational forces could lead to the formation of distinct universes with unique physical properties. Take, for example, the work of theoretical physicist Max Tegmark, who posits that different realities could emerge from the variations in the fundamental constants that govern each universe. Under this framework, gravity is key to determining the structure and fate of each universe, which could range from those where stars and galaxies exist normally to those devoid of any matter or energy at all. Moreover, black holes serve as critical hubs for investigating the interplay of gravity and parallel universes. When matter is compressed into a black hole, the laws of physics as we know them break down, presenting a tantalizing possibility. Black holes could act as gateways to other universes, or even lead to the birth of new ones. Stephen Hawking's groundbreaking theories on black holes indicate that they emit radiation, known as Hawking radiation, which might eventually allow for the escape of information that could traverse into another universe. Hawking's hypothesis sparks the imagination, leading to the exciting idea that black holes might not be ends, but rather beginnings, venturing into parallel realities that operate under different physical rules. This notion aligns with the speculative idea that each black hole could contain a separate universe, growing and evolving independently of our own. Experimentalists are also working on probing the influence of gravity on the multiverse theory. The research surrounding gravitational waves, ripples in spacetime caused by massive astronomical events, holds profound implications. When gravitational waves propagate, they could potentially carry signatures of interactions that hint at the existence of parallel universes. Additionally, the recent detection of gravitational waves by LIGO has opened a new field of inquiry within astrophysics, suggesting that these waves might carry traces from events that occurred in different universes. The possibilities for harnessing this data are immense, as it could offer unprecedented insights into the fabric of reality and the multiverse. As we delve deeper into the relationship between gravity and parallel universes, the implications are profound. We may begin to understand how gravitational fluctuations could create conditions that support varied realities, effectively redefining our comprehension of existence itself. Consider this: if gravity is a bridge connecting our universe with others, what might exist beyond the veil of our reality? Could there be universes where gravity operates differently, shaping entirely new forms of matter, energy, or life? These questions invite us to reimagine what we know about the cosmos, propelling us towards an exciting frontier in scientific exploration. In conclusion, gravity is a vital component that shapes and differentiates parallel universes. Its intricate connection with spacetime and potential influence on other realities illuminates unexplored territories in our understanding of the universe. As humanity delves deeper into the mysteries of parallel universes, an intriguing question arises: what role does consciousness play in this cosmic tapestry? Throughout history, philosophers and scientists alike have pondered the relationship between the mind and the universe, leading us to explore uncharted territories of cognition, perception, and reality. One perspective regarding consciousness and parallel universes lies within the realm of quantum physics. The famous physicist Eugene Wigner proposed the idea that consciousness itself might play a critical role in the collapse of quantum wave functions, essentially, that our observations shape reality. This view aligns with the many worlds interpretation, whereby every observation we make spawns a split in reality, leading to the existence of multiple outcomes based on different conscious choices. Consider the implications of this thought. If consciousness can shape the very fabric of reality, then could the collective consciousness of humanity influence the existence and interaction of parallel universes? In this scenario, our thoughts, intentions, and beliefs might reverberate through multiple timelines, crafting variations of ourselves across different realities. Philosopher David Chalmers has explored the nature of consciousness and its profound mystery, offering the idea that consciousness could be a fundamental feature of the universe itself. He proposes that there may exist a relationship between consciousness and the multiverse concept, suggesting that perhaps our awareness is intrinsically linked to the existence of alternate realities. This perspective challenges conventional notions of separateness and nudges us to consider a more interconnected existence. Examining ancient wisdom, we find parallels in various cultural and spiritual traditions. Many belief systems emphasize the significance of consciousness transcending physical boundaries, hinting at the possibility of parallel existences inhabited by different iterations of oneself. For instance, reincarnation beliefs suggest that the soul may journey through different lives, potentially across different universes. This ancient worldview resonates with contemporary ideas regarding the multiverse and consciousness. As science progresses, research into consciousness is gaining momentum, with studies in neuroscience, psychology, and cognitive sciences examining the mechanisms underlying our perception of reality. Recent findings from studies of altered states of consciousness, such as lucid dreaming or near-death experiences, offer tantalizing glimpses into the interrelation between consciousness and the multiverse. Could these experiences provide evidence of our entanglement with parallel realities? One fascinating case study involves the phenomenon of déjà vu, a feeling that one has experienced a situation before. Some neuroscientists theorize that déjà vu might entail the brain processing alternate realities, suggesting that moments of overlap between different timelines could yield these uncanny sensations. The implications are profound. If consciousness is indeed a bridge between universes, every choice we make may resonate across different facets of our existence. As we ponder the intersection of consciousness and parallel universes, we are reminded of the power and potential of the mind. If our consciousness shapes reality, then it beckons us to realize our agency in crafting the multiverse itself. By embracing our interconnectedness and understanding the implications of our choices, we embark on an exciting journey towards self-discovery and cosmic exploration. In conclusion, the exploration of consciousness and parallel universes invites profound questions about identity, existence, and the nature of reality. By recognizing the interconnectedness of our minds and the cosmos, we open ourselves to the possibility of shaping not only our lives but the very nature of the multiverse. Time travel has long captivated the human imagination, from H.G. Wells' classic novella The Time Machine to modern films like Interstellar. But what if time travel holds the key to understanding parallel universes? In this chapter, we will explore how theories of time travel may not just bend our perceptions of time but also influence the very fabric of reality itself. The concept of time travel raises numerous questions about causality and the nature of existence. Imagine a world where traveling back in time creates a branching universe, where every choice generates another timeline. This is the basis of the many worlds interpretation of quantum mechanics we discussed in previous chapters. One fascinating example of this idea comes from physicist Kip Thorne, who worked on the theoretical aspects of time travel for the film Interstellar. Thorne's research suggests that if we could create a wormhole, potentially linking 2 points in space and time, it could allow us to traverse not only distance but also time itself. This raises the possibility that stepping through such a gateway might lead us to a parallel universe that closely resembles our own, but with crucial differences. However, leading scientists like Stephen Hawking introduced the chronology protection conjecture, positing that the laws of physics may prevent time travel to avoid paradoxes. Can we alter our past without splitting the universe? To illustrate these ideas, let's delve into the story of physicist David Deutsch, who proposed the first theoretical framework for time travel involving quantum mechanics. Deutsch argued that if we could travel back in time, our interaction with the past could create branching timelines, each representing different potential outcomes. This concept is more than a thought experiment, it has real implications for our understanding of time. In a practical sense, the concept of time travel invites us to ask profound questions about the universe. Could we meet different versions of ourselves in alternate realities? Or, when we make decisions, are we just one thread in a vast tapestry of existence? In summary, time travel and parallel universes challenge our fundamental understanding of reality. As technology advances, our capacity to explore these complex ideas may lead to new insights, and perhaps one day, the ability to witness their wonders firsthand. As we move on, we will explore how the search for extraterrestrial life intersects with the multiverse hypothesis. What might other universes reveal about life beyond our own? Art has always reflected humanity's deepest curiosities and fears. In an age where the existence of parallel universes is a legitimate scientific possibility, How do artists interpret these ideas? In this chapter, we explore the intersection of art and the multiverse, examining how artists across various media convey concepts of alternate realities. From Salvador Dali's surreal landscapes to contemporary digital installations, the visions of alternate worlds provoke our imagination and inspire our understanding of existence. For instance, consider Dali's iconic The Persistence of Memory, where time is represented in a fluid and distorted manner. This piece can be seen as a precursor to multiverse theory, questioning the rigidity of our reality and suggesting that time and space can take on myriad forms. In modern art, artists like Robert Rauschenberg and Yayoi Kusama play with the ideas of infinity and multiple perspectives, often creating immersive environments that challenge viewers to question their perception of reality. Furthermore, film and literature have embraced multiversal themes with fervor. The film Everything Everywhere All at Once illustrates the chaos of infinite possibilities in a witty yet profound way. This cinematic exploration of the multiverse resonates with audiences as it reflects our innermost dilemmas and alternate life choices. Additionally, writers like Neil Gaiman have woven multiversal threads into their narratives, creating fantastical worlds where different versions of characters explore their own identities. Gaiman's American Gods showcases characters torn between multiple realities, drawing parallels to the very real existential questions we grapple with. Through these artistic expressions, we can perceive the multiverse not just as an abstract scientific theory, but as a canvas reflecting the complexities of human experience. We grapple with our choices, identities, and the infinite possibilities that lie before us. Each piece of art invites reflection: what hidden universes reside within our own lives? By examining the intersection of art and the multiverse, we recognize that both seek to answer fundamental questions about existence. Our exploration of this connection reveals a shared curiosity, fostering a broader understanding of what it means to be human in a universe so vast and mysterious. Next, we will delve into the scientific implications of parallel universes on the evolution of consciousness. How do different universes shape who we are? As the field of multiverse research continues to expand, we must confront the moral and ethical implications of our discoveries and pursuits. Should we actively seek to explore other universes? Can our actions here impact those realities? In this chapter, we will delve deep into the ethical landscape of multiversal research, considering both the potential benefits and hazards it may bring. At the heart of this discussion is the responsibility of scientists and researchers in dealing with powerful theories. For instance, physicist Brian Greene has emphasized the need for caution in exploring the multiverse. He argues that we must respect the boundaries of science and ethics as we push the frontiers of knowledge. Consider the ramifications if we were able to access alternate universes. Would we be tempted to exploit resources from those worlds? Could our presence pose risk to the delicate balance of those realities? Historical incidents like the colonization of new lands on Earth illustrate humanity's propensity to exploit unknown territories, often with devastating consequences. Moreover, ethical dilemmas arise when we consider the potential for manipulating fundamental aspects of existence. If we could alter our timeline or influence parallel beings, would we have the right to make such decisions? Psychologists argue that awareness of multiple realities can shape our moral compass. As we navigate our understanding of existence, the prospect of infinite possibilities may lead us to question our own actions more deeply. For example, the notion of a multiverse of moral actions suggests that every choice might create diverging paths, making us more mindful of our responsibilities. As we venture forward in multiversal studies, we must collectively establish ethical guidelines. Countries and institutions must engage in discourse to balance scientific pursuits with moral considerations. How do we ensure that in our quest for knowledge, we do not cross boundaries that could have ramifications far beyond our understanding? In conclusion, the exploration of parallel universes not only fuels scientific inquiry but also ignites ethical questions that demand our attention. As we look into the cosmos, let us consider the weight of our actions and choices, both here on Earth and beyond. Next, we will discuss the role of technology in enhancing our understanding of the multiverse. How will the future shape our exploration? Time travel has long fascinated humanity, inspiring countless novels, films, and philosophical debates. But what if time travel is not merely a science fiction trope, but a legitimate concept that intersects with the theory of parallel universes? Understanding the implications of time travel requires us to delve into the fabric of spacetime and the role of quantum mechanics. One of the most compelling concepts tied to time travel is the idea of closed time-like curves, which allow for the possibility of traveling back in time within a specific universe. This concept, first proposed by physicist Kurt Gödel in the 1940s, suggests that under certain conditions, such as in the vicinity of a rotating black hole, one could theoretically loop back to an earlier point in time. However, this leads us to the classic paradox of time travel, notably illustrated by the grandfather paradox. If one were to travel back and alter a crucial event, would they still exist in the new altered timeline? To extrapolate this further, if time travelers were to navigate the multiverse, they wouldn't simply affect their own timeline but could potentially shift into a parallel universe altogether. This means that a decision made in one universe could create an entirely separate reality where a different outcome occurs. For example, if a time traveler went back and prevented a historical event, the original timeline would still exist, but a new timeline, where that event never occurred, would branch off. This branching model aligns with the many worlds interpretation of quantum mechanics, fueling discussions among scientists about the mechanics of how time travel might allow access to parallel universes. When we consider how quantum particles behave, we see that every decision a particle makes can lead to a new universe. An electron that goes left could create one universe, while one that goes right creates another. Many scientists like physicist David Deutsch and futurist Michio Kaku posit that advances in quantum computing and entanglement could one day unveil pathways through time and parallel universes. Imagine a future where technology allows us to access these alternate realities, a tantalizing idea that blends science fiction with science fact. While we may still be far from practical time travel, understanding these concepts ignites our imagination. It poses significant philosophical questions about choice, consequence, and our understanding of existence across time and space. How would knowledge of alternate timelines affect our decision-making in the present? Would we act differently if we knew we could explore those branches of reality? As our understanding of quantum mechanics deepens, the boundaries of time and space may prove to be more malleable than we ever thought possible. Could we step into a portal and emerge in a universe where we made different life choices? What emotions would we grapple with if we encountered alternate versions of ourselves? While the mechanics of time travel remain speculative, they challenge us to rethink the very nature of reality. As we conclude this chapter, we find ourselves on the brink of possibilities that stretch the limits of our imagination, leading us to the next chapter, the intersection of art and the multiverse, where creativity meets scientific exploration. Art has always mirrored society's most profound questions about existence and reality. From ancient myths to contemporary narratives, artists explore themes that resonate deeply with fundamental inquiries about our place in the cosmos. As we delve into the multiverse theory, we see how the intersection of art and science not only fosters creativity but also profound philosophical exploration. Consider the works of Salvador Dali and his surrealist explorations. In paintings like The Persistence of Memory, Dali captures the fluidity of time, an idea that aligns intriguingly with the concept of time in parallel universes. His dreamlike landscapes evoke questions about perception and reality that are rooted in the very scientific concepts we explore today. Modern filmmakers have embraced the multiverse concept with fervor. Movies like Everything Everywhere All at Once present a narrative that leaps between alternate realities, exploring themes of identity, choice, and consequence. This film resonates with the multiverse theory, showcasing how divergent paths can lead to unimagined outcomes. The characters grapple with their decisions in a manner that reflects our understanding of parallel universes, making audiences ponder their existence in a myriad of realities. In literature, the multiverse concept has been explored by authors like Neil Gaiman and Haruki Murakami, who weave intricate narratives that challenge the boundaries of reality. Gaiman's The Sandman series, for example, explores dream worlds that exist parallel to our own, inviting readers to rethink their perceptions of reality. Moreover, visual artists utilize the multiverse to provoke thought and inspire dialogue. Installations that represent alternate realities challenge the viewer's notion of existence. Artists like Yayoi Kusama create immersive environments that evoke feelings of infinity, echoing the vastness of the multiverse and our tiny place within it. In the realm of music, composers like Philip Glass and Max Richter explore similar themes, crafting soundscapes that invite listeners to ponder the nature of time and existence. Their works evoke emotions that resonate deeply with the scientific themes we've discussed. As we analyze these creations, we see that